Let's take a moment and go through the conceptual background information for the vapor pressure lab exercise. For all liquids, when they're below their boiling point, a small fraction of the liquid will always start to turn into gaseous particles. Now, as gaseous particles are formed, more and more gas particles go up into the airspace. Some of the gas particles eventually will bounce into the liquid, and when they bounce into the liquid, they turn back into the liquid phase. Now, for a liquid, as we increase the temperature, the amount of particles that would become gaseous becomes greater. Now, in a closed system, eventually we reach a point, and a closed system could be something such as our classroom, where it's isolated and we have a set volume, or it could be something such as a beaker with a top on it or a bucket with a top on it. But in a closed system, eventually what takes place is that the amount of particles becoming gaseous, and then the amount of gaseous particles that are bouncing back into the liquid reach a complete balance, and they're in what we say a state of dynamic equilibrium, where the rate at which gas particles is forming is exactly the same as the rate at which liquid is reforming. When this happens, when we have this state of balance, the rate at which the liquid's turning into gas is exactly the same as the rate at which the gas is turning back into liquid. It's once again referred to as a state of dynamic equilibrium. Now, the special thing about dynamic equilibrium is that the amount of particles that are gaseous is now remaining constant. Now, the particles that are gaseous, which because we have this balance and we're in a state of equilibrium, the particles are staying constant. Because they're gaseous particles, these particles can create pressure, which in the volume of the gas. The pressure that's being created by these gaseous particles when in a state of dynamic equilibrium with the liquid phase is specifically referred to as something known as the vapor pressure of that liquid. The vapor pressure of a liquid is a specific quality for that liquid and unique to any given liquid. The vapor pressure, again, is the point at which we have this dynamic equilibrium. The rate at which liquid is turning to gas and the rate at which gas is turning back into liquid have become the same. This gaseous space is saturated with the gaseous particles that are coming from that liquid, in that there's not any room for any more additional gaseous particles at that particular temperature. And because the particles are in the gas phase, those particles can create pressure within the volume in which that gas exists. That pressure that gets created by these gaseous particles that are in a state of dynamic equilibrium with the liquid phase, and in which the gas particles have completely saturated the airspace with those particular gas particles, the pressure that they create is something specifically known as the vapor pressure, or PVAP, for a particular liquid. The conditions necessary to reach this state of vapor pressure for a liquid are rather specific. If a container is open, as the particles become gaseous, the gas particles leave the container, and a state of equilibrium is never established, and we cannot reach a state of dynamic equilibrium and achieve the vapor pressure. Or if there's an insufficient amount of liquid available to saturate the airspace with gaseous particles, in that as the liquid becomes gaseous, all of the liquid ends up evaporating to form the gas before the state of equilibrium is reached, this would have a situation where the gaseous space is not yet saturated. We've reached some pressure, but it's going to be lower than the vapor pressure because the system isn't saturated yet with the maximum number of gaseous particles for that particular liquid. To reach, once again, what is referred to as the vapor pressure of a liquid, it has to be the specific conditions and circumstances where the liquid becomes gaseous, and then some of the gas returns to liquid phase, the rate at which the gas is turning to liquid and the liquid is turning to gas becomes exactly equal. The gas space becomes what we refer to as being saturated with the maximum number of gaseous particles for that temperature. We have a state of equilibrium, and then the pressure that's created from these gaseous particles is referred to as the vapor pressure for that liquid. Now let's continue and look at a system that is, once again, it's saturated, where the amount of gas particles that are in the closed system is the maximum we can have at a given temperature. We refer to this as a saturated system. The system's at equilibrium, and that the rate at which particles are making gas is the same at which gas particles are turning back to liquid. This would create what we call the vapor pressure of the system. Now for this system, let's say we're at 25 degrees Celsius and the vapor pressure of our particles is 100 millimeters mercury. If we now take the temperature of this system and increase it, what's going to happen for all liquids as the temperature goes up, more particles can now become gaseous at a now higher temperature. If more particles become gaseous, what happens is as temperature goes up, the vapor pressure of a liquid also increases because we can now have a greater number of particles present in the gaseous space when it reaches its saturation point. So in this case, let's say we went from 25 degrees and we've increased it, say, 50 degrees Celsius. The vapor pressure might have now gone up to from 100 to 300 millimeters mercury because there are now more particles that are in the gas phase at the higher temperature. If we continue to increase the temperature, more and more particles continue to become gaseous, creating a greater number of particles that are in the gaseous space when the system is saturated and at the state of equilibrium. With more particles, the vapor pressure continues to rise, and this would be true for all liquids. As temperature goes up, the number of particles that can become gaseous goes up. The number of particles, if the number of particles that's gaseous is increased, more particles are hitting the sides of the container, the pressure would increase. So for all liquids, as temperature goes up, the vapor pressure also increases. As the temperature increases, more particles become gaseous. Now as the temperature goes up and up and up, eventually the vapor pressure, when it becomes equal to the outside pressure, which is typically in Darien about 760 millimeters mercury, or 1 atmosphere in pressure, when that takes place, when we hit the temperature at which the vapor pressure becomes equal to the pressure that's above the liquid from the outside conditions, this is when, by definition, boiling occurs. This is actually the definition of boiling point for liquids. As we increase temperature, more particles become gaseous. As more particles become gaseous, the vapor pressure of a liquid gets higher. Eventually, when we reach a temperature when the vapor pressure becomes equal to whatever the pressure is on top of the liquid from the room or wherever the liquid may be, that's the point at which boiling takes place and is the definition of boiling point. There's also a connection between the vapor pressure of a liquid and the strength of the intermolecular attractive forces that exist for the molecules that make up that liquid. For example, let's consider these three liquids, X, Y, and Z. All three are at the same temperature. Liquid X has weak intermolecular attractive forces, Y has medium strength, and of the three, Z has the strongest intermolecular attractive forces. Now, all liquids will have some particles that can go from liquid to gas. Now, given that these are all three at the same temperature, the compound that has the weakest intermolecular attractive forces, compound X, will have the most particles that become gaseous. Compound Y would have fewer particles that become gaseous at the same temperature, and Z would have even fewer particles. Reason being, weak intermolecular attractive forces require less energy for the particles to separate themselves and turn from liquid to gas. Medium intermolecular attractive forces require more energy for the particles to be separated from liquid and turn to gas. And strong intermolecular attractive forces require even more energy for the particles to be, if you will, break those intermolecular attractive forces and separate the particles so that they behave as a gas. Now, the consequence of this is that by the time each of these systems reach a saturated gaseous system where it's at a state of equilibrium and we reach the vapor pressure for each liquid, even though they're all at the same temperature, the vapor pressure for each liquid will end up being different. The compound with the weakest intermolecular attractive forces has the most particles that become gaseous when it reaches the saturated equilibrium system. So compound X would have the highest vapor pressure at this given temperature. Compound Z would have the lowest vapor pressure at this temperature. And compound Y would have some vapor pressure that falls between compound X and compound Z at this particular temperature. Now, the strength of the intermolecular attractive forces not only affect the vapor pressure of the liquid, but also the boiling point of the liquid. In that as intermolecular attractive forces get stronger, more energy is required to cause the particles to separate from each other and sever those attractive forces. And if more energy is required, that's reflected by a higher temperature is required to cause the particles to separate and become gaseous. So let's say hypothetically in this scenario that the pressure over all these liquids, we're in Darien, Illinois, the pressure over the liquid is 1 atmosphere. For boiling to occur, that's when the temperature of the liquid reaches the point when the vapor pressure of the liquid becomes the same as the pressure of the liquid over the liquid. This will be reflected in each liquid's boiling point in that with the highest vapor pressure is going to have the lowest boiling point because it requires the least amount of energy to reach the point where the number of particles in the vapor phase creates pressure that's equal to the outside pressure in the room. The compound that has the lowest vapor pressure, because it has the strongest intermolecular attractive forces, would be the liquid that has the highest boiling point. The medium attractive forces would give us a medium temperature for a boiling point. Now, the process of causing a liquid to turn into a gas for all liquids requires the input of energy. We have to add energy to a liquid to cause the attractive forces between the particles, the molecules in the liquid, to sever, and the particles then become gaseous. The input of energy makes this process what we call an endothermic process. If we look at this graphically, another way to depict it is that the liquid form of this is at a lower energy state than the gaseous form, which is true for all materials. Liquids are a lower energy state than the gaseous form. And the energy we have to put in a system would be the difference in energy between the gaseous state and the liquid state. This difference in energy for chemical processes is known as delta H, or the change in enthalpy of the reaction or process. Now, for endothermic processes, the delta H is a positive number. And specifically, when we're turning a liquid to a gas, the delta H is referred to as delta H of vaporization. The heat of vaporization, also known as delta H vap, is the energy required to convert a liquid to a gas in the endothermic process of adding energy to a liquid to provide sufficient energy to overcome the attractive forces between molecules in the liquid, cause them to separate, and turn the liquid into a gas. In our lab exercise, the specific goal is for us to experimentally determine the value for delta H vap, or the energy required to go into liquid water to convert this into gaseous water. Now, because water has fairly strong intermolecular attractive forces, since water can form hydrogen bonds, the amount of energy we'd expect to find here will be fairly high compared to other liquids with weaker intermolecular attractive forces.